say a part of the boiling and condensation until say 7th and 8th. Okay, so you may see that we will be more or less like catching up with the syllabus once again. And tutorial 5 and 6, tutorial 4 and 5 will feature in quiz 3, and 6 we will take up in the exam examination. So that's the way things are laid down. Okay, if you have any question, you can ask right now. You have any question? Any doubt? So the whole summary of the whole story is that next Friday we will have a lecture. If we are through with the syllabus, then second we have a tutorial, or if we are not through with the whole thing, then second we will have a lecture, and third we will have a tutorial. Okay, and then 7th and 8th we will have a quiz. Right. So tutorial number 4 and quiz number 2 will be finished by 8th of November. That is the objective right now. Meanwhile, the lecture classes I'm going to announce as and when. Right now, we are having a class on Friday. We'll have a class on Monday. We'll have a class on Tuesday. And Tuesday we'll decide we'll have a class on Friday or not. Okay. And you are submitting tutorial 3 on coming Friday, correct? Tutorial 3 you are submitting on Friday 30th. I know before the class. Okay. Okay. Now let us progress with the lecture. So 44 students, just request, Shreyanshu request everybody to join ASAP. Okay. Yeah. So let me share my lecture slides. So right now we are going to discuss about, up to this point, what we were discussing. My slides are visible. Am I correct? Can have somebody confirm?
Yes.
Yeah. Yeah. Thank you. So up to this point, we were discussing about the flow which is on a flat plate or flow which is inside a conduit. So what do I mean by a conduit? Say, suppose if I really think about a say, if I really think about the geometry, we were discussing about a kind of like flat plate like this, and on top of that there is a flow that is taking place. This is the most common geometry that we have discussed, and then what we did, we went for a conduit. This is called a conduit flow. It can be, say, two very long and infinite parallel plates, or it can be a kind of pipe. It can be a kind of tube. So I'm drawing a kind of center line here. So these are the two specific that we discussed, two specific geometries that we discussed over a period of time. The flow and the consequence associated with the heat transfer. The flow and the consequences of flow on the heat transfer. This is what we have discussed. Today we are going to focus on another very interesting fluid mechanical object, or a heat transfer associated with a fluid mechanical system, that is flow past immersed bodies. Okay, what is a flow past immersed body? Say, suppose you can see there is a diagram that is given, right? So what is this diagram? This is typically the cross section of an airfoil, okay, or aerofoil. What is an aerofoil? Aerofoil is an aerodynamic shape of what? Say, suppose this is the wing of an aeroplane, okay, and you can see the cross section of this. The wing of an aeroplane, it looks like this. And why is it done so? Because there is a reason we do this sort of thing. As you progress in your fluid mechanics course, you will learn that this particular process is called streamline. I could have gone for a circular geometry, but I'm going for this sort of geometry. I could have gone for a kind of flat channel-like geometry, but I'm going for this sort of geometry. Why am I going for this sort of geometry? This particular aspect is called the streamlining of a geometry. Okay, and we are going to study what are the effects of this different geometrical structures and streamlining associated with them on the fluid mechanics and heat transfer. So by now you have more or less understood that heat transfer is a very close and intertwined subject with fluid mechanics, And why is that so? Because heat transfer processes, or most of the heat transfer processes, they involve the motion of a fluid. Okay, so in that situation, you may think about that. Say, suppose this is the wing of an aircraft, and the aircraft is moving at a very high velocity. So the air is flowing on top of that. Now this air is undergoing friction here. Okay, so there is a viscous dissipation. So this structure is typically the flow structure that is happening. This is typically called the shedding of the air. Shedding of the fluid air around this streamlined velocity is a typical turbulent profile that takes place. This is what you see, when the jet goes, and then you see two different to a couple of ejections that are following a kind of jet. That happens because of this type of aerodynamic structure, this type of a fluid mechanical structure that are generated around the flow of a aircraft or around the wing of a aircraft. Right now, this is an immersed object. This is the fluid flow. That's why this is called the flow past the immersed bodies. So the focus of the lecture today is the forced convection, or the features of the convection, or the features of the fluid mechanics on the heat transfer associated with the flow past the immersed bodies. Great. Now, what we realized from the past few lectures, okay, although all the equations that we did were a bit complicated, but then what we realized that if we start with a simplified Navier-Stokes equation, so this these are the convected terms, this that this is the diffusion term, this is originating from the friction, this is originating from the convection, these are all convective accelerations, and this is after enforcing the Newton's law of viscosity in the Cauchy's equation of motion. Okay, so this is my x directional equation of motion. U that actually tells me that it's an x directional steady state equations of motion, and there is no pressure gradient, and this is my continuity equation. Now, in this equation, if I enforce two orders of magnitude for a boundary layer. For a boundary layer, what is the thickness? Y is equal to delta. Delta is my thickness, and u equal to u infinity. This is my free stream velocity. Now, if I enforce these two dimensions in this continuity equation, I may get u infinity by x equal to v by delta. If I simplify this equation, from there I can get v equal to u infinity delta by x. Okay, and now say for a flat plate, this x is very, very large, and you can really imagine that v is essentially very, very small for a unidirectional flat flow. Now, if I put this order of magnitude back into this equation, okay, into the momentum equation, so I get delta square equal to nu x by, if I simplify this entire thing, so I get delta by x equal to delta square equal to nu x by infinity, or delta by x equal to 1 by root over RE. So doing a very simple order of magnitude analysis, I can really prove that the thickness of the boundary layer with respect to the length of the plate is nothing but a inverse function of Reynolds number power half. Okay. So we were doing a lot of mathematics. This is another trick, an order of magnitude analysis to arrive at the same equation. So what is this delta? This delta is nothing but what we were discussing is the thickness of this boundary layer. Okay. What is this RE? RE is the free stream velocity. RE is the REX is the based on the average velocity in the boundary layer. What is the Reynolds number? Okay. Now, what are we are calculating the thickness of the boundary layer is the inverse function of the Reynolds number to the power half. Okay. And this is the dimensionless boundary layer thickness. So this we have been doing for last 3-4 classes very extensively. So just I thought to revisit this because after a gap, you may be forgetting some of the things. Just to tell you that this is not that far away. I mean, you need not remember even. You just plug in some magnitudes and you will be able to really get back. Okay. Yeah. Now, we could really appreciate from last few lectures that what we were fitting, basically we were fitting a Nusselt number which is equal to a constant with Reynolds number to the power an exponent m and Prandtl number to the power an exponent n. Okay. So people thought that since these equations are very, very difficult to solve analytically, and you can really have to work hard in order to get analytical. So suppose if I think about set of these two equations, right? Even for set of these two equations, this is a hyperbolic equation, by the way. Okay. And say suppose you have this continuity partially. So it's a two-dimensional set of partial differential equation with all appropriate boundary conditions today. You will not be able to really solve. There is one attempt that has been made by Blosius, okay, to solve this equation for Blosius boundary layer, but that also is a semi-analytical solution. That not you will read in fluid mechanics that is also a kind of semi-analytical solution. You cannot have an analytical solution for this sort of equation with proper boundary condition associated with, say, suppose a flow like this, right? So people thought that since we are getting very simplified correlations associated with the boundary layer and its thickness and Reynolds number, in engineering calculations, you can really make very good approximate, models using the correlation called the Nusselt number, which is the ratio of the convective to conductive heat transfer, equal to Reynolds number, which is the ratio of the inertial to the viscous forces, and Prandtl number is what? Momentum to thermal diffusivity. This is actually telling exactly the boundary layer is diffusing across, how exactly heat is diffusing across the boundary layer, how exactly hydrodynamic thickness is increasing across the boundary layer in a diffusion due to the molecular motions. This actually tells you what is the ratio of the convection to conduction, convection to molecular momentum diffusion, and this actually tells you how exactly heat is convected to how exactly heat is molecularly conducted. So now, if you look at this equation, there were multiple varieties of this sort of equation has been created for a range of Prandtl number, Reynolds number. Okay, different types of effects. I'm coming to this d by L and mu by mu W. Essentially, for a given system, what you do, you go for a kind of plot which is, say, suppose Nusselt number to by Prandtl number to Reynolds number. So, it's a log plot, and you can see that you perform a number of experiments based on the free stream velocity, based on the fluid viscosity, based on the thermal conductivity of the material. Okay. And then, evaluate the heat transfer coefficient. And then what you do, you fit in those experimental values in order to obtain these experiments. Now, when you did that, you could identify that one particular correlation, which could really explain a lot of different experiments, which is called the Ditas-Coulter equation. So you just need to remember that Nusselt number is equal to, say, 0.023, Reynolds number to the power 0.8, and Prandtl number can be 0.4 or 0.3. Okay, so 0.4 is for a heating fluid, 0.3 is for a cooling fluid, right? Now, this particular correlation can be used if you do not have any correlation for a given flow. This particular equation can be used extensively, for any unknown system that you are looking forward to. Okay, and how this particular correlation is obtained? This particular correlation is obtained by doing a number of experiments around these dimensionless numbers. So there is no physical law associated with this. This is just a correlation. This is just something like, say, Newton's law of viscosity, that stress is proportional to strain, or the Hooke's law of motion, that stress is proportional to strain. Newton's law is strain rate, stress is proportional to the strain rate, right? How did people arrive to this? These are called phenomenological correlations. How did people arrive to this correlation? The people performed a number of experiments, and from a number of experiments, they plotted certain value, and from there they could arrive that, okay, this set of fluids, they follow this correlation. That sort of fluid, they follow that correlation. Okay. Now, you may see that this equation is the heart of the whole game. And this is arising from, after performing a few analytical calculations, we could see that most of the patterns of this type of correlation is emerging like this for a forced convection situation. Okay, that can be simplified to a very generic form like this. And whatever additional effects are there, you can take with the effects of, say, suppose mu is the viscosity of what? Mu is the viscosity of the bulk, and mu is the viscosity at the wall. What is the situation here? Say, suppose you have a pipe flow taking place, and in the pipe, say, suppose this is one that is inlet, that is TB1, and this is the 2 that is outlet, where you have TB2. So these are two different temperatures, and at the same time, the bulk of the fluid has a particular temperature, and the wall of the fluid has a particular temperature. What is the situation here? Suppose this is a heat exchanger. So there is a hot fluid here, and this hot fluid is being cooled by the cold fluid that is going inside. So I can imagine near the center line, the fluid temperature will be very, very low. And I can imagine the temperature near the boundary should be very, very high. Now, if that is the case, then I can expect that mu that is there in the bulk will be a little bit lower, and mu near the wall, sorry, mu in the bulk will be a little bit higher, and mu near the wall will be a little bit lower. Why? Because the wall is heated up. So your viscosity will be a little bit less. You know that if I increase the viscosity, if I increase the temperature, viscosity reduces. And as I go towards the center, when there is a cooler fluid, viscosity will be higher. So this is a kind of a very typical situation associated with this sort of flow. Okay. So in this situation, how do I do? What is the heat transfer? It is mCp Tb minus T1. So this is very much, this is mCp is M is the mass flow rate, Cp is the specific heat constant pressure, and Tb minus T2 is the temperature difference. But this can also be written in a differential form as what is dq? dq is mCp dTb. dTb is the temperature change in this shell. Okay, which you know that this is a convection process taking place. This is now trivial for you. AHA into delta T. This is A, this is H, and delta T. So you can write Q is equal to HA, TW that is at the wall temperature, and T bulk that is at the bulk temperature, right? Now for this equation will be valid. But then if you really want to incorporate the effect of the viscosity that is in the bulk and viscosity that is in the wall, so this particular equation can be made a little bit more accurate with some experiments. Okay, how? Is essentially it is done like, so suppose if you have done a number of experiments using these pipes, and you saw that this type of exponent come for this sort of situation. Okay, now you may see that this Dieter's-Bolter equation, where you put Re to the power 0.8, Prandtl number you put always 1 by 3, which is in between 0.4 and 0.3. That means 0.33333. What was the wisdom in the previous case? This you are talking about Re to the power minus 0.5, right? Now, say suppose in case you evaluate Nusselt number from here, you will see that the Reynolds number exponent will also come like this, that we have evaluated in the previous classes. So the gist of the story is that for this type of flow, this is a pipe flow, conduit flow, we can correlate the flow with using the Dieter's-Bolter equation, where we will say that Nusselt number is equal to 0.0223 equal to E into Reynolds number to the power 0.8 and Prandtl number to the power 0.333333. That is the equation that we are going to typically remember, right? And whatever special effects are coming, say suppose mu bulk and mu W, D by L is the entrance effect. Why is it coming? You know that from fluid mechanics that this flow, when it enters in the pipe, it is the all free stream velocity, but due to friction it will develop into a parabolic profile like this, correct? Now because of heating and cooling, you may also see there is a change in the temperature, change in the velocity profile owing to the change in the viscosity. See, you can see that mu is the bulk viscosity and mu W is the wall viscosity. So you may see liquid heating, gas cooling situation may lead to a flow pattern like this, and gas heating, liquid cooling may lead to a flow pattern like this. So this parabolic profile also may change due to heat transfer, which can be correlated to the effect of mu by mu W or D by L. Okay, and that can also be described using this Dieter's-Bolter type correlation. Just keep this in mind, because this will also be important when somebody is joining a kind of design company, and when you are designing extensively the heat exchangers, these heat exchangers are designed for what? Say suppose for Boeing, Airbus, okay, different ships, Korean companies, who manufacture different types of ships, okay, European companies for Boeing, and then Airbus for US companies, different types of automobiles, they have lots of different types of heat exchangers, okay. So in those heat exchangers, this type of correlations are used while designing them. Okay, so suppose Schlumberger is a company where, like, if you join, they will design this type of heat exchangers. So suppose EIL, Engineers India Limited, is one company. It's one of the PSUs, who has this expertise in designing these heat exchangers, designing these different types of evaporators, condensers, where you may require the usage of these correlations. Now, one can very easily see that it is not only to do with the Nusselt number, Reynolds number, and Prandtl number, to do with the friction factor. And this perhaps you are going through in your fluid mechanics class, that the friction factor is a function of what? Reynolds number. And in laminar domain, you know that this is 64 by RE. The derivation is pretty much straightforward. What is friction factor? Say suppose if you have a wall and if a fluid is flowing, there's a friction between them, and this friction factor, which is called in laminar domain the fanning friction factor, is the measure of how much loss you are incurring. So the interesting part is that as you keep increasing the fluid flow rate, what happens? The friction reduces. Okay, the friction reduces. However, beyond the transition domain, as you go from laminar to turbulent domain, so there is a sudden jump in the friction. However, for smooth pipes, as you keep increasing the Reynolds number, what is happening? What happens? The friction factor reduces. And we have discussed about this because this has to do with what? This has to do with the boundary layer thickness. Correct? Say for a laminar flow, the boundary layer thickness is very high in case of and speed is very low when the velocity is very low. But then what happens? Then as the velocity increases, as you increase the velocity, what happens? This thickness of the boundary layer changes, and that has a very big correlation with what? That has a very big correlation with the friction factor. Now, another important aspect that you see on the right hand side, this is called the Moody's chart. On the right hand side, this is called the roughness. So if the pipe is rough, okay, so what happens with the roughness of the pipe? You can see that the friction increases, right? Remember that this is a log-log plot. So even if it is a linear, that means in normal plot this will be following a hyperbolic correlation. This is one very important plot which is asked by in your interviews. That's why I kept them in the lecture, because this will be helpful. So keep these slides with you and revise them before your interviews, because this will be one chart which generally people ask during the interview, that what is Moody's chart? Okay, so Moody's chart is friction factor versus Reynolds number plot. Okay, where in the turbulent domain you have different lines associated with different roughness. Okay, this was performed by a scientist his name is Nikuradze. He created this plot just by performing n number of experiments in pipes which are smooth, at the same time in pipes which are rough. So how did he generate the roughness on the pipes? So he took a pipe and then he put sand, he bombarded sand on the wall of the pipe. So how you do that? Generally, how you create a pipe, you take a steel sheet and then you roll it to make a pipe, right? So what he did, he took sheets of different sizes, and while these steel sheets were made, what he did, he put sand particles of different size on these pipes, and then he rolled these sheets into pipes. So he could create pipes of different roughnesses. And then he performed experiment just by looking at, he kept first, he created a pressure head. The Bernoulli's equation, including the friction factor. So he applied a pressure drop. He had a dynamic head, and from there he could evaluate the friction factor. And those friction factor he plotted against the Reynolds number at different roughness of the pipe. So this particular plot has been generated by a scientist. You can understand how many experiments. I think he was a German scientist. He performed in order to really identify that what will be the friction factor for a pipe in the laminar domain, what will be the friction factor for a pipe in the turbulent domain. Okay, how will it look like in the transition zone? You can see there is a discontinuity. Okay, and what will be the influence of the roughness? Okay, so now if you really remember the traits of the plot and all. So you have one question that is common in your interview. So please study this chart very, very carefully, because these are the things that are in general asked as fundamental questions in your interviews. Great. Now you see that moment I talked about friction, friction also comes into picture in terms of this Nusselt number versus Reynolds number, Prandtl number plot for different situations. I have just given you the slide to go through and see that for convections, for heat transfer also, you really bring in the influence of the friction factor, especially for the pipes which are rough in nature. Okay, especially for the flow which are turbulent in nature. And these predictions, this line is very, very important. Typically, these predictions are nearly about 20 to 25%, erroneous. Okay, if you really go for a full-fledged analytical calculation, since you are using a kind of very simple model here, okay, you end up doing a kind of 20 to 25%, you allow 20 to 25% error, which is called the engineering error. One major essence of engineering that you should understand, that you need not do something with a kind of like n precision accuracy. Okay, but then engineering calculations are rather ad hoc calculations, and those ad hoc calculations are supplemented by one thing called over design, right? So since you are incurring a kind of 25% error, you are incurring a kind of 25% error at this stage. So what you do, you just make sure that you over design for about 30%, when you are designing with these correlations. So this is the reason why I have put this slide, to tell you that different types of Nusselt number, Reynolds number, Prandtl number, Stanton number correlation, Peclet number correlations are available with you. But these correlations are to be handled very, very carefully for specific situation, and while finalizing the design, these calculations are ad hoc calculations, and you have to account for the over design. Okay, and that is where the engineering genius comes into picture. That's, suppose if you look at Saraighat Bridge, this is hanging since 1966. Okay, say more than 50 years this is hanging, and there is no major calamity. Now, the design has to be there, the material management has to be there, cost has to be minimized, but there should be adequate over design so that all the safety measures are taken into account, right? So you may see that in different correlations, the effect of friction factor comes in, the effect of temperature comes in, effect of roughness comes in. Okay, so just to give you the example how exactly they go about it. Great. Geometry also has an effect, right? And geometry has been converted to what? So a parameter called the hydraulic diameter. Different types of geometries you can think. This has a diameter, but these people do not have a diameter. So what you do, you get an equivalent diameter, okay, which is called the hydraulic diameter. So 4 into area, this is called the flow area by the weighted perimeter. So if you divide flow area by weighted perimeter, you get a flow area by weighted perimeter, you get a diameter. Okay. So in that process, you make sure that 4 into area. So suppose for a sphere, this will be 4 into area means 4 pi r square, 4 pi r square. Okay, divided by what? P will be weighted perimeter will be what? 2 pi r. So if you divide that, then what happens? This becomes 2r. So 2r means the diameter. So for a sphere, this will be d. So similar way, one can really calculate different hydraulic radiuses for a rectangle, for a hexagon, for a square, for a triangle, and then you can really modulate your Nusselt number and friction factor using these hydraulic diameters. Okay, now entrance effects. In order to take care of the entrance effect, you define a parameter called Grei's number. Okay, what is a Grei's number? Grei's number is Reynolds number into Prandtl number into d by x. What is the entrance effect? Say suppose the flow has entered here as a plug profile, and as it goes to downstream, it becomes a parabolic profile. So slowly the friction is increasing as I am going downstream. Okay, slowly the boundary layer is developing and the heat transfer is taking place. So this is the diameter and this is the length of the channel, and the d by x means this diameter to length at which it develops the fully developed profile, right? So if you multiply the Reynolds number and Prandtl number with d by x, that is what is called the Grei's number. D is the diameter, x is at which length it is getting the fully developed profile, right? So the effect of entrance effect for any fluid flow heat transfer is taken care of by the Grei's number. So what you do, you plot the Nusselt number with respect to the Grei's number. Okay, what you are doing here you are doing with respect to, here you are doing with certain Nusselt number with respect to Reynolds number into Prandtl number, or Nusselt number by Prandtl number with respect to Reynolds number. in order to get the correlation, in order to get the Dietz-Bolte correlation. If you really want to consider the entrance effect, what you need to do, you go for Nusselt number divided by what? Divided by the Grice number, or Nusselt number into at x divided by Nusselt number infinity to x by d. It's a very similar thing from here to here. It's not very different. It's a different types of plots that are shown for an example. So if you look at it, you will see that they are more or less same. So this gives you the effect of, say, suppose if a fluid flow is developing, that effect also can be taken into account in these correlations. Great. Now, once we are done with that, now we see that how these theories can be extended to the flow past immersed bodies, right? What is a flow past immersed body? Say, suppose I have a sphere, and say, suppose I am flowing a fluid, and there is a flow pattern that is generated around the sphere. Why this particular problem is important? Because this is a model system. Say, suppose you want to know what is the loss associated with the drag in a car. Why it is so important? Because you are burning petrol in order to move the car. Say, suppose you are going from your home to college, right? So you are burning X amount of fuel from going from home to college. But then, why you need to burn the fuel? Because, you need to run it. Okay. In addition, what is happening here while running, you are incurring losses because of the friction that is associated with this fluid and this object. So suppose this is your car and suppose this is your fluid. So if it is moving in this direction, this air is going in this direction, and in the process, you are encountering a force which is called the drag force. So as you start running, what happens? You want to move forward, but then, there is a moment you start running, there will be a drag that will be dragging you back. So what is the reason for any flow that is taking place? Suppose this air is flowing from this direction to this direction. It happens because of a pressure head, right? And if I apply a pressure head across say, suppose a geometry, or say, suppose a particular space, then what happens? What is the consequence of that to the fluid? Moment I apply a pressure head, I am going to get a dynamic head, right? Now, this dynamic head is assumed to be proportional to the drag force. So rho u infinity square by 2g, this is called the dynamic head. Okay, the kinetic energy. Say, suppose if you have applied delta P, so it is going to flow the fluid at u infinity. So you say that the kinetic energy associated with that is per unit volume is rho u infinity square by 2gc, and that is proportional to your drag force. Okay. Now, the proportionality constant comes as CD. So what do you say? That force is proportional to the area. Area means the projected area. What do I mean by projected area? Projected area means through which the fluid is taking place. So for this, you can see that for a sphere, this is a circle. Okay. For a bottle like this, if the flow is taking place like this, if you take a cross section, if you cut it vertically, the plane that comes up, that calls the projected area. So drag force, you say that you define phenomenologically, just the way you define the viscous forces. Okay, drag force you define phenomenologically. Say suppose it is proportional to the area, and it is proportional. More is the area. More is the area. Say bigger. If you have a bigger size, okay. If your body size is bigger, you will have more. Why? Of course, since it is a friction, more area means the force will be higher. And what is the other aspect? More is the velocity, more will be the drag. Okay. Why? Because if I try to move faster, then I will attract more fluid around me, and that will lead to the so the dynamic head associated with the force and the area, you say that drag force is proportional to this. So you get a correlation FD equal to CD is the proportionality constant into A into rho infinity square by 2gc. This is what is called the drag force, and CD is called the drag coefficient. A is called the frontal area. Frontal area means not this area. Not this area. Area means if I take a cross section from here and the cross section comes, so in case it will be a circle. Okay. Even for a cylinder, what will be the flow area? If I see if this is a sphere, it will be a circle. If I take a cylinder, what will be the flow? A will be a rectangle. Okay. So in that process, this A is called the frontal area or the projected area. Now, this becomes a model system. Typically in a wind tunnel, all these experiments in wind tunnel in aerospace labs, you will see that there'll be a air source, there'll be a compressor which will be compressing air and forcing the fluid at a very high speed, and then you have an object through which you measure, you image and measure different types of flow patterns that are generating around this particle. The flow is taking place because of a pressure head, so you are generating a dynamic head, and very interesting thing happens. The flow will initially creep on the surface, okay, and will generate a kind of half parabola type velocity profile. Is a kind of development of boundary layer. But if the flow is very fast, or if this slope is not streamlined, then you encounter a situation which is called the flow separation, right? So we are going to discuss about that as we progress in the next slides. So what is the condition for flow separation? You may see that if the flow profile is like this, the flow will not separate. But if the flow profile is going from here to here, so there is a kind of black backflow, that means the flow separation will take place. And this condition has been defined as, at this particular point, if your du dy the slope is equal to 0, beyond which the flow separation will take place. Okay, so we understand from this slide that flow past cylinder or a flow past sphere is the model system to study all the aerodynamic, all the fluid dynamic aspect associated with drag. And then we have to deal with two things. One is the drag force and the other is the flow separation. So what happens, if I take a sphere or if I take an infinite cylinder and if I have a very low speed flow, this particular flow is called the creeping flow. Creeping flow means what? The fluid will come like this. At this particular point, stagnation point means the fluid velocity will become 0. On the wall of this sphere, the fluid velocity is 0. So the flow will creep like this and then will go like that. So this is what is called a creeping flow rate. But if I increase the Reynolds number to 10, what will happen? Say at this particular point, I will find this del u by del y to be 0. And the this fluid will go like this. This fluid will go like this. This streamline will go like this. This streamline will go like this. Now, moment it goes like this, there is some fluid at the back side. So if it goes like this, the fluid that is there, that is adjacent to this, will go in this direction. But then, this is going in this direction. Now, these two vortices will create a kind of recirculation zone at the back side of the sphere. These are called the twin steady vortices that will be created. Okay, twin steady recirculation zones that will be created here, while the other portion will undergo a creeping flow. And this particular point will be called the separation point. Now, if I increase still the Reynolds number, what will happen? These separation points will start oscillating. So this will go down a little bit, like say suppose this. See, this is called a typical phenomena called von Karman vortex state. So separation point was like this. Now, if I increase the flow rate beyond a certain point, the separation points will start oscillating in a time periodic manner. These 2 points will start oscillating in a time periodic manner. If it goes here, it will go back. If it comes here, it will go back. Now, if that happens, then there is a phenomena that will take place that is called shedding. So one vortex will be ejected from here while this will go back. Then the next vortex will come from this side while this will go back. And in the process, you may see there is a von Karman vortex state at the downstream of the backside of the sphere. Now, if I further increase the Reynolds number, what will happen? So this is the transition domain. This is the laminar domain. This is the separation point. Okay, this is the transition domain. These two basically are the transition domain. And then what happens at 10 to the power 4? I may see that there is a complete separation of this point, say suppose near the poles. However, if I increase the Reynolds number further, what happens? These separation points will go more towards the downstream of the geometry. So you may see that there is a constriction. There is a kind of forcing of the boundary layer, while at the entire back of the downstream of the process, where you will see the turbulent wake. So this is the typical chart of Reynolds number variation, flow past variation of flow, different flow patterns, across a flow past immersed body. Examples why we are studying this, you may see I have given so many examples for you. Say this is a typical tennis ball. Say when Roger Federer and Nadal are serving, so you can see that what is a typical Reynolds number? It is about 10 to the power 5 2 into 10 to the power 5, 1.6 into 10 to the power 5, right? Now, in that sort of situation, you may see that that sort of turbulence behind when this is traveling. So you just remember this thing. There are, see, when you serve, no, the ball is traveling, air is stationary. But when we perform experiment, we make the ball stationary and then we blow the air. This is an inverse experiment that we are performing. This is the way the volleyball is served, right? So you may see that the trajectory goes like this, correct? Now the trajectory goes like this because of the change in the different types of flow patterns across this. Say suppose this is your this golf ball, okay, which has got this dimple around it. So you may see a kind of flow profile like this. And how these flow profiles are done? So you just put some smoke in air, and then you do high-speed imaging in order to see the flow profile that is at the backside. So this is again for a tennis ball. Okay. Now this is around a cricket ball. So one very interesting thing that happens for a volleyball or a tennis ball. Okay, tennis ball, this top spin, right? So you see that Nadal has a lot of top spin, and that's why Nadal is more or less unbeatable. He has won so many Grand Slams. What is the reason? Because he has got top spin. Top spin means what? This ball rotates at a very high speed. Now you imagine that there is a fluid flow that is taking place, and this ball is also rotating at a very high speed. So what it will do? It will, say suppose it was supposed to go like this straight, right? Or it is going to come down like this straight. But if you can rotate it, what will happen? Because of the rotation, it will develop some lift, and then it will dip. So the trajectory will become very, very complicated, and it will be with the rotation. If you can control the rotation, with the rotation, you can drop it here, you can drop it here, you can drop it here. And then your game becomes very, very unpredictable for the opponent who is here, who is anticipating where the ball is going to dip. So this happens for not only tennis, this happens for football. Okay, this also happens for a cricket ball, right? Now the seam position actually decides, okay, it is going to swing in which direction. So there is called a conventional swing and there is called a reverse swing. And what is the situation here? You may see that in case of a new ball, this part is smooth, this part is also smooth. So if you just make the seam a little bit angular, what happens? You have a turbulent boundary layer here at a very high velocity, whereas you don't have that boundary layer here. So there is a pressure drop across when the ball is traveling like this. If the seam is like that, so there is a pressure drop across the seam, and that is the reason why, or while going like this, it is deviating either in this direction, based on the seam position. Right? Now, in case of a reverse swing, which happens at a much higher velocity for the fast bowlers, what is that? The ball is old, and you have two rough surfaces, around the seam. So when you have two rough surfaces around the seam, so suppose you are shining one of the sides. So now if you force it at a very high velocity, what happens? Now since one of them is shined and other is very rough, you generate two rough boundary layers across this, and then again there is a pressure drop, and that is the reason why it goes for a swing with the old ball. So you can see that a lot of fluid mechanics that can be really figured out, can be thought of. People have studied this, the baseball structure. So all these balls, cars, they make different types of movements based on the flow profiles that are happening around a particle, and which has a very far-reaching consequence associated with. There is a very far-reaching consequence associated with what? Associated with the heat transfer associated with the process. Yeah. So what is that? First, let us understand. Say, suppose if there is a creeping flow, if there is a flow separation, if there is a von Karman street, laminar boundary layer, and then turbulent profile, how this drag coefficient that changes with Reynolds number. Okay. How, from where this drag coefficient is coming? From drag force is what? CD into half rho v square into A. This is what we have defined already, right? Now you see that when there is no separation, it is high friction zone. But moment the separation takes place, the friction is little less. For von Karman vortex street, it is still less. And then for turbulent boundary layer, laminar boundary layer with a turbulent wake, there is this laminar sublayer, and this wake is turbulent. In that sense, more or less the drag coefficient remains, more or less flat. And then as the boundary layer shifts towards this thing, Okay, when the boundary layer also becomes turbulent, then you see there is a rapid reduction in drag. Okay, so if somebody asks you that, say, suppose you have an object and then you want to really put that object into motion. So at which velocity your fuel burning will be least? So if you look at this plot, which is Reynolds number versus a drag coefficient, you will see that if I run my car, okay, at this Reynolds number, in this situation, my drag will be minimum, right? That's why when you travel in a car, the driver is always trying to get into fourth gear, fifth gear. Why? Because if you are going to fourth gear and fifth gear, you are typically going at a higher speed into this domain where your drag coefficient is minimum. And then you will see that all the car owners will advertise the cars with respect to what? Now, what is the mileage? When you go, you see two different points. Number one is power. What is the power of the engine, and what is the mileage? What is the power associated with the engine? That how much energy you can generate per unit time. That gives how fast you can move. Okay. Now, second is what? Second is how much mileage does it give? Mileage means per kilometer, per liter, how many kilometers it can go. Now, say suppose if you have a car which has a drag of this, and suppose you have a car at optimal velocity drag of this, and optimal velocity drag of this. Of course, the car which at optimal velocity will have a drag of this will have less fuel consumption and more mileage, and that's where will be more economic for you in terms of day-to-day activities. And typically, you are told that you drive a car between 40 to 60 kilometers per hour. The prescription at fourth gear is given based on the minimum of the drag coefficient, right? So this is the fluid mechanical aspect of it. Okay. Now, of course, this is a non-streamlined shape. This is a spherical shape, and if you look at a streamlined airfoil type or aerofoil type shape, so here you may see that this boundary layer is laminar. At the downstream, the boundary layer becomes turbulent, and at the backside you have a viscous wake, and you try to move your aircraft under this condition. Why? Because in this sort of situation at high speed, your fuel consumption is minimum. The aircraft need to get into this steady state as soon as possible in order to reduce the operating cost. So it is moving at a free stream velocity where there is a viscous wake, where most of the boundary layer is turbulent boundary layer, and you cannot avoid this laminar boundary layer because this will anyway be developing as it encounters the air, right? And this is happening only near the aircraft wing or the aircraft geometry. Even aircraft geometry, you will see it will look like this. There will be a nose. Okay, why there is a nose? You try to really reduce this laminar boundary layer, because this is where you are losing most of the fuel in terms of friction. Now, once you understand this and the physics associated with this separation point, what is the physics that is associated with this separation point, this separation point, this separation point? That if you apply a pressure drop at some point of time, if you develop a flow profile like this where del u by del y equal to 0, at this stage also, see, typically if del p by del x is less than 0, you develop a flow profile. So here the pressure is higher, here the pressure is lower. So del p by del x, p is low, p is high, that means del p by del x is negative. Now, at the separation point, what happens? Del p by del x is equal to 0, which also enforces del u by del y equal to 0. And while this undergoes a backflow, and this leads to separation in a situation where locally backflow means here the pressure is high, here the pressure is low. That means del p by del x is greater than 0. This is the condition for the flow separation. Now, once you are through with that, you can really design different types of nozzles where this is a developing flow, and then in this sort of situation you have del u by del y is equal to this situation. You have del u by del y is becoming negative, and del p by del x is becoming positive, and you can really see kind of flow separation, right? Now, in those sort of situations, you may see the Reynolds number versus. So this is for a circular cylinder. This is for a circular cylinder, and this is for a sphere. So you may see these are the more formal plots. So you will try to reach try to reach a domain which is this, where your drag coefficient is minimum. So you try and make geometries, you try and create operating conditions for which the drag coefficient is minimum. And this has a very far-reaching consequence in terms of your heat transfer calculations, right? So for a flow past immersed body, you see your Dittus-Boelter equation. Okay, this also has the correlation associated with this theta is the, see, these are all you are now doing in terms of what you are doing in terms of, see, correlation for heating and cooling in cross flow over circular cylinders. So earlier what we were doing on a flat plate. Okay, this is local Nusselt number for heat transfer from a cylinder in a cross flow. Okay, so here what you're doing, you're trying to see the fluid mechanics, the flow and the heat transfer associated with the flow past immersed bodies. And you can see different types of correlations again are cooked up for different types of geometries. Nothing to be remembered here, but just to be aware that which equation you will use for which condition. Now, while you saw the flow profiles there, these are all the temperature profile. Today with COVID pandemic that this IR sensors can measure the temperature of your forehead, right? So similarly, the temperature around a immersed body while the fluid flow is taking can also be imaged. So this is a hot object maybe, and then around that there is a fluid flow taking place, and that fluid has different types of temperature. So you can really see the temperature profiles in the form of imaging. Okay, at different Reynolds number. These are all different types of isotherms that you can see from the grayscales. Okay, so non-circular cylinders, they follow this type of correlation, right? In the case of low pass immersed bodies, you can have a bank of tubes like this. Okay, where the distance between this is SP, the distance between this is the parallel ones, this is the normal ones, this is the free stream velocity. Okay, these are all arranged in a very ordered manner. This is in an eclipse manner, this is in a staggered manner. So you can really calculate the U max that is there inside this as U infinity to these geometrical parameters. And a lot of calculations have been done for these tube banks to decide this constant and this exponent. Okay, and the numbers, right? So in line, this is in line, this is staggered. So different types of correlations you will see will be available for, for this is a very famous Zukaoka's correlation, okay, which is for these banks, the pressure drop calculation, friction factor calculation at the same time, the calculation of the Nusselt number to Reynolds number. Finally, in today's lecture, this is the example that I was talking about. See, in every situation, the hydrodynamic boundary layer will not be thicker than the thermal boundary layer. There are situations where thermal boundary layer will be thicker than the hydrodynamic boundary layer. Example, say suppose if you have a liquid metal that is flowing on a substrate, right? So liquid metal, that is extremely thermally conducting. So heat will transfer much faster than the development of the boundary layer flow, right? And in that process, what will happen? Your thermal boundary layer will be much thicker than the hydrodynamic boundary layer. Now, how do you arrive? You again enforce the same boundary layer equation. You assume a kind of parabolic profile. Okay, basically for power series for theta infinity, and then if you obtain the boundary layer thickness, so you end up getting delta is your hydrodynamic boundary layer, delta T is your thermal boundary layer. You may see that delta by delta T will come out to be about 0.16 when your Prandtl number is 0.01. So what does it mean? That your hydrodynamic boundary layer is a part of the thermal boundary layer. Earlier we were discussing the equations where your thermal boundary layer is always fraction of the hydrodynamic boundary layer. So this is a situation liquid metal transfer where heat transfer where you can see that thermal boundary layer can be thicker than the hydrodynamic boundary layer. So in this process we really finish the discussions associated with the forced convection. Okay, natural convection will start in the next class, followed by radiation and the evaporators, design of the evaporators and heat exchanger. So and boiling condensation. These are the 4 topics that are remaining. So essentially, we are finishing the 6th chapter today, where what we have studied in the 5th and 6th chapter. What we have studied? We have studied that for a convective system, you develop boundary layers. These boundary layers are different for a flat plate, for a tube, and for a particle. Okay. Now, in that, what is the framework to decide? It is the Nusselt number to Reynolds number and Prandtl number, right? Now, this Nusselt number to Reynolds number, Prandtl number comes under a Dietz-Boelter framework, okay, with certain modifications for different types of geometries, like say suppose a bank of tubes or a kind of like heated pipe. Okay, so the small modifications are there, but essentially the framework remains that Nusselt number is equal to constant into Reynolds number to the power m and Prandtl number to the power n, where m and n are typically 0.8 and 0.33 for a Dietz-Boelter correlation. Right now, say suppose if you are flowing a fluid, there will be a hydrodynamic boundary layer, there will be a thermal boundary layer. Now, for a pipe and for a flat plate, you can do semi-analytical calculations in order to evaluate the thickness, the Reynolds number, the Nusselt number, and the heat transfer coefficient. Now, you have all this parameter, you are able to really make the design associated with how much heat transfer will be there. Okay, so we stop here. So 6th chapter we have finished. We have finished up to 6th chapter, and I'll try and finish the 7th chapter in the next class. So up to that point, we will make sure that our quiz 2 is conducted until 7 and 8 on 7 and 8. Okay, and we will have a class on Friday. Have any questions? Open for some questions. If you have any questions. Any question do you have? So I hope all of you are receiving the YouTube videos, correct? All the lectures are uploaded, right, Shreyanshu? So I'm going to share this presentation also with all of you. Pratu, all the presentations are uploaded, right? And they are given like
Yes, sir. Everything is there.
Great, fantastic. So this also you include, okay? And so we meet on Friday. So once again, since now everybody is there, we're very happy Dasera to all of you, and stay safe and stay healthy. Okay. Yeah, thank you. Thank you so much for your attention. So the syllabus for the quiz is, we will decide. I will announce on Friday's class the syllabus for the quiz. Okay. Thank you. Thank you so much.